They're talking about current evaluations that I probably shouldn't opine on. So
Are you recording?
I'll make sure I put this part up on YouTube. All right.
Well, they can answer in the comments. Just
Hey guys, just answer in the comments below. Make sure you like and subscribe and ring that bell. Oh my God, that would get me in so much trouble. What's that? It's there. I'm recording it. Oh, totally. Right. So the first question I got. So what we're going to do, sort of in the next part of the class, which starts today, is we're going to talk about linear algebra. So it's going to be weird because we spent a bunch of time learning basic differential equations, and then we're going to leave it alone and do something entirely different for 3 or 4 weeks, which is going to seem kind of weird, but there are reasons for that. I'll remind you when we get to that part. Before we do that, I did get an interesting question in the last class about what the point of even first-order differential equations were. Like, what's an application that is used in practice? And so I thought I'd write one down because there's actually a really nice one that you can write down. So all of you that are currently experiencing or have experienced a Physics 1 class have learned kinematic equations for motion, right? And in particular, you probably spent some time with free fall diagrams. And so sort of classic free fall, which is, we're thinking of the last thing we're doing here. This is an application of first order linear differential equations. You learn sort of Newton's second law, so force is equal to mass times acceleration. Acceleration could be a function. It could change with respect to time. And so sort of a real basic picture of an object that is falling. It's acted on by a force of gravity, Fg. Since it's downward oriented, we think of this as the sort of positive direction, and this is the negative. I'm going to write this as minus mg to indicate that the force is pointed down in my coordinate system. And with that, I could write down minus mg is equal to ma. If I want to think about a as a function, I think about a as being the derivative of velocity. So I could write this as mg is equal to m times dv dt, which is a dumb first-order differential equation, but it's definitely a first-order differential equation. The m's even cancel, and you get the differential equation dv dt is equal to minus g. You don't need to use any fancy techniques on this one because you can just integrate it. And you get the solution, v of t is equal to minus gt plus c. So what that model says, this particular model of free fall that we derived from the second law, says under this assumption of falling, under this model, velocity of an object increases forever. If you jump out of an airplane at 30,000 feet, you hit the ground at like 15,000 miles an hour or something because you go faster and faster and faster and faster. Of course, that is not at all what actually happens, right? What actually happens when an object falls is that it hits, you can physically observe that there's a maximum speed that it hits. So this model is not a very good one. This is free fall in a vacuum. And a more sophisticated model can be derived. Now that we've got the tools to solve it, we can derive a model that involves air resistance or drag we can put in the picture. Now, because this is a course in linear differential equations, we have to make a pretty big simplifying assumption about the behavior of that. But if you have free fall with air resistance, now you have some mass m. Say it's falling, same coordinate system, so positive up and negative down. It's still being acted on by gravity, Fg. But now there's going to be a resistive force acting against its velocity, right? So we'll call it Fa for the force of air resistance. And what Newton's second law here would say would be that mass times acceleration as a function of time would be equal to the sum of these forces. Fg I've already modeled because I'm calling this minus mg. So m times a of t is equal to minus mg. And now we have to make a choice. And the first choice that we frequently make when we're modeling air resistance that gives us anything like a realistic picture of how objects fall is I make the observation that FA is equal to minus KV, which is to say air resistance is proportional to velocity but in the opposite direction. So the constant of proportionality K here is a measure of sort of, you can think about it, how many feathers you're covered with, right? If you're spread out like a flying squirrel or you're a smooth ball. So your K is your sort of drag coefficient. And a very simple model of air resistance says the faster you're going, the more air resistance you're going to feel. Right? That's essentially what that says. The negative sign is here to make sure that this force is always in the opposite direction of velocity. So what that gives you is a simple model of fall subject to air resistance, which is m times a of t is equal to minus mg from the force of gravity minus kv, where now v is a function. And so now I've got m times dv dt is equal to minus mg minus kv. And this is a differential equation, a linear differential equation, because there's a v prime and a v in it. I'll point out for those of you that have already seen this or are going to go on that a much more realistic model for this is FA is proportional to velocity squared. But we don't have the tools to solve that right now. So typically this is handled by numerical solvers anyway, but that's what put us in the land of nonlinear differential equations, which we can't solve. But it's worth taking this simple picture of air resistance because we're going to compare the output of the initial model where there was no air resistance and compare it to the solution we get when there is. So if I rearrange this, I get m dv dt plus kv is equal to minus mg. You should recognize that as a first-order linear equation. It's not quite in the correct form to use an integrating factor on yet because there's something stuck onto the v prime term. So if you divide everything by m, you get dv dt plus k over mv is equal to minus g. And now we're all set up for hitting this with an integrating factor. So I of t is equal to e to the integral of k over m dt. That's just a constant. So you get e to the k over mt as your integrating factor. If you multiply the equation through by e to the km over t, you will arrive at d by dt of e to the k over mt times v is equal to minus g times e to the k over mt. So I've just taken my initial equation here and I've multiplied through by my integrating factor. I'm going to integrate both sides to get rid of the d by dt. That will give me e to the k over mtv is equal to, okay, so that's a constant, those are constants, and you get minus gm over k e to the k over mt plus c. If you use the chain rule here, you can see that the k over m pops out and kills this m over k. And the last step is to divide both sides by e to the k over mt, which gets us v of t is equal to, okay, that goes away, minus gm over k plus c times e to the minus k over mt. So let's take a minute and interpret what that says. So minus g over mk is a constant, a negative constant. So it's oriented down. That says velocity with respect to time has this thing that's always there, this constant term. And what happens to that term as t goes to infinity? Yes, e to the minus infinity, which goes to 0, right? So the limit as t goes to infinity of v of t is equal to minus g over mk. And this is what we call terminal velocity in this model. So the introduction of the resistance term mathematically builds in this idea that there's a terminal velocity in the model. So you shouldn't think that somehow we've magically uncovered the secrets of the universe. It's that this is a model that exhibits similar behavior to what we see in the physical world. And so it's a reasonable model to use in many cases, right? So this is a choice for a model that includes a choice for a resistance term for air resistance And the solutions to that model exhibit the behavior of terminal velocity. So in a lot of ways, this model is a more realistic one than the sort of free fall in a vacuum that you learn in your physics 1 class, right? But the reason you don't learn the more sophisticated model is you don't have the tools to solve the equation, right? They just give you the answer without actually telling you why it's true. So, okay. And again, yeah, so you can, I'm boxing both of these so you can compare how different the solutions are with the introduction of just a single additional wrinkle to the model that we picked up wildly different behavior in the nature of the solutions. Right? So the sensitivity of a model to the inclusion of extra terms is pretty high. Okay, questions about this? Sweet. Let's do linear algebra. So one takeaway that you might have from a picture like that is, well, if I just have, what if the coefficient of friction changed as speed changed? That also can be a function of time. You could have all kinds of things wiggling around in a model like this. And the more pieces you put in your model, the more sophisticated it gets, but the more complicated it is to analyze. Okay. So we are pivoting out of differential equations to talk about linear algebra. So remember, here's sort of our goal. This is what we want. So we have two different generalizations of differential equations we want to work with. We want to work with second or higher order stuff. So I need to be able to handle equations like y prime prime plus 3y prime plus 2y is equal to 0. To understand the solutions to second order equations and make sure that I've got the entire picture of what those solutions look like. And then I also want to be able to handle systems of differential equations. So here you can imagine maybe you have rabbits and the rabbit population with respect to time, well, it grows exponentially. So there's some constant proportionality times the number of rabbits there actually are. So this is like dr dt. The rate of change in the population of rabbits is proportional to the current rabbit growth, which would be exponential growth. But then they're being eaten by foxes. And the number of foxes that there are, well, they have some underlying base rate of reproduction. But also, their growth rate is really high when there's lots of rabbits and really small when there's fewer of them, right? So I want to actually have another component here that, like, this is the rabbit eating piece, right? The more rabbits there are, the more foxes there are. But the more foxes there are, the fewer rabbits there are. So this is a simple system of differential equations that describes two interacting populations. So R and F here are functions of time. But notice that their differential equations are combined with each other. And the idea is, this is the setup that linear algebra is basically built to handle. It's scenarios like this. So we're going to learn a bunch of linear algebra for weeks. And then we're going to revisit both of these cases for the sort of last third of the class. We're going to have the tool set that we need to understand what's happening in both of these pictures. Okay, so if this seems weird and like we're taking this huge left turn in totally new material, that's because that's what we're doing. So 2.1. So this is just terminology. So we're talking about matrices. Now, the goal in all of this, I'm going to have a lot of terms to write on the board, a lot of technical definitions today. Essentially, our goal is we are going to want to write down the equivalent of this type of idea. If I gave you an algebraic equation, and I ask you to solve it, the first thing you would do in this equation is you would add 1 to both sides, and you would get 2x is equal to 7. And the next thing you would do would be what? No, there's no such thing as division. Yeah, I trapped you. You multiply by the multiplicative inverse. I was hoping somebody would give me the answer. So really what I do here is I multiply by the multiplicative inverse of 2, because there's no such thing as division. And when it turns out that the multiplicative inverse of 2 is equal to 1/2. And so I get x is equal to 1/2 times 7, which is 7/2, right? So I algebraically extracted the answer with steps involving addition or subtraction across an equal sign, and then multiplication by the multiplicative inverses of things, which let me sort of isolate a variable or an unknown. What we're going to want to do, and I'm not going to make this concrete until the end of the class today, if then, is ultimately we're going to be solving equations that look like AX is equal to B, where this is a matrix, this is a vector, and that's a vector. So we're going to be building the algebra of matrices today. So that's kind of the beginning point here. And that means that the move that you want to make in an equation like this would be to somehow divide by A, which you would mean by multiplied by its inverse. But in order to get there, I have to define what a matrix is, what matrix multiplication is, how you add matrices, and we will not be here today, but like what the inverse of a matrix is, if it even exists, and what the solution set looks like. So everything we're doing today is related to stuff that you saw in earlier classes when you did systems of equations and you decided if they were consistent or inconsistent. And if they were consistent, they could have a unique answer or infinite answers. All of that is encoded in what we're building up to. All right. So some of you, this is going to be review until we get up to actually calculation of inverses, I think. So a matrix is an array. So a 2D array. For those of you that are programmers or computer scientists, this is the most important part of the whole class. It's the next 4 or 5 weeks. So a matrix is a 2D array of numbers. So for example, I could write down A is equal to 2, 0, 1, 1, 3, 1. That's a matrix. Its size is 2 by 3 because there are 2 rows and 3 columns. If I wanted to write that matrix down abstractly, I could write down A is equal to A11, A12, A13, A3, A21, A22, A23. I can index each entry by its row and column position. So each entry here, if I think of A12, this is the entry that is in row 1, column 2. So this is typical notation for a matrix, is to look like this. If I want to take that even further and indicate a 2 by 3 matrix without writing down a grid of variables like this, I can go one step further and write something like A is equal to a matrix of entries where I goes from 1 to 2 and J goes from 1 to 3. That's about the most abstract way you could write down a matrix. If you've taken a basic computer science class, you've seen arrays probably set up this way. Or the book might just write this, and you guess the size of the matrix. So, in this matrix over here, so if I write down something like A is equal to 1, 0, 1, 2, 2, 1, 3, 6, 1, 1, 5, minus 9. And I ask you for the A32 entry. What is it? A32 is equal to 1. I can also think of a matrix as being constructed from a set of row vectors. So I could think of this matrix A as also being a row vector, row 1. And then another row, row 2, and then another row, row 3, where row 1 is equal to 1, 0, 1, 2. It's called a row vector because it's set up long ways instead of tall ways. Alternately, I could think of A as being constructed of 4 column vectors. A could be thought of as column 1, column 2, column 3, column 4. Where, say, column 1 is 1, 2, 1. So matrices are usefully thought of as being chopped up into all kinds of these sort of arrangements. I can think of A as a collection of row vectors. I can think of A as a collection of column vectors. So, since we're going to do algebra with matrices, so the point of doing this notation right here with columns and rows, this is how we're going to define matrix multiplication when we get there. First, we should talk about adding things. So if A and B are matrices of the same size, then A plus B is equal to, check this notation out, Aij plus Bij. Yeah. All that means is you add two matrices of the same size by adding the entries in the same spots. So 1, 0, 3, 2, 1, 1, plus 2, 0, 6, 1, 9, minus 10 is equal to, they're the same size, so I'm just going to add the stuff that's in the same positions. This is called entry-wise addition. So 1 plus 2, 0 plus 0, 3 plus 6, 2 plus 1, 1 plus 9, 1 plus negative 10, which would be 3, 0, 9, 3, 10, minus 9. So matrix addition requires them to be the same size. In fact, you could think about this as being related to the stuff we did with vectors, where if vectors were the same size, we could get two vectors and get another vector of the same type back again. This is kind of the same thing. This is how you would do it if they were vectors, right? Stuff in the same entries is attached to the same sort of structure. So the other operation that we could do that relates to vectors is we can define what's called scalar multiplication, which everybody knows. So if K is a scalar, A is a matrix, then Ka is the same as K times Aij, where I goes from 1 to m, J goes from 1 to n. And the way you do scalar multiplication is you just put the scalar inside. So that's the abstract version of the rule. It's much less confusing to see it written out. 3, 1, 2, 3, 4, 5, 6 is 3 times 1, 3 times 2, 3 times 3, 3 times 4, 3 times 5, 3 times 6. The same way it would be if we were working with vectors. You just push the scalar inside. 6, 9, 12, 15, 18. Okay, so already this should be reminding you of the way vectors work, because we've done, these are both operations we've seen before, and for those of you that weren't in the class when we did vectors, almost certainly you've seen vectors in some context earlier in your life somewhere. There is an operation that we can do to combine these two ideas that you may or may not have seen the word for before. It's going to be really important in here, so I'm going to define it. So a linear combination of matrices A1, A2 up to AM is a sum C1A1 plus C2A2 out to CMAM, where C1 up through CM are scalars. So if I have a bunch of matrices of the same size, I should say here of the same size, and I hit each matrix with a scalar, and I pile them all together with addition, that's called a linear combination. So linear combination is one of these ideas that we're not going to be able to escape for weeks. The last operation I should show you before we define matrix algebra is the idea of taking the transpose of a matrix. It shows up in some more sophisticated calculations. So the transpose of A is a matrix called A with a T up top, like it was power, so A to the T, with whose columns are the rows of A. So the transpose of a matrix just switches rows for columns. So if I took A was equal to 1, 0, 1, 2, 6, 3, A transpose is 1, 0, 1, 2, 6, 3. The rows of A become the columns of the transpose. The columns of A are the rows of A transpose. All right, two more pieces of vocabulary before we go on to talking about some mathematics. A matrix, so the main diagonal, so a matrix is square. I'll just say it this way. A square matrix is n by n, so same number of rows and columns. The main diagonal of a matrix is the entries A11, A22, A33, and so on. So if I wrote down A is equal to 3, 1, 3, 0, 1, 2, 6, 1, 4, then the main diagonal of A is this. Main diagonal. The last two bits of terminology here are a matrix is diagonal if it's square and it only has non-zero entries on the diagonal. A is called a diagonal matrix. If A is square and all non-zero entries are on the main diagonal. So for example, 1, 0, 0, 0, 0, 2, 0, 0, 0, 0, 3, 0, 0, 0, 0, 4 is a diagonal matrix because anything that's not 0 is located on the main diagonal. These are some of the most special types of matrices. We also have notions of what are called upper and lower triangular matrices, which will be important when we start doing Gaussian elimination. If you've seen Gaussian elimination before, it's going to come back with a vengeance in here. But in a better way probably than you learned before. So if I write down a matrix that looks like this, 1, 2, 3, 4, 0, 1, 2, 1, 0, 0, 3, 6. This matrix is called upper triangular. Because all of its entries below the main diagonal are 0.
Does it have to be a square to have that?
Nope.
Or is it not?
All entries below. Yeah, I'm doing this on purpose.
What's its main diagonal then it's not a square?
A11, A22, A33. So the main diagonal of a non-square matrix you can still think about as being the set of entries that start in the upper left-hand corner and go until you run out of entries that have that form. Right? Are 0. The square matrix is easier to pick out. If I give you a matrix A is equal to 1, 0, 0, 2, 1, 0, 0, 1, 3, that matrix is called upper triangular because all of the entries above the main diagonal are 0. Sorry, lower triangular. This is upper triangular because everything it's 0 below the main diagonal. A lower triangular matrix has 0 entries above the main diagonal. This is lower triangular. So another characterization of diagonal matrices is they are upper and lower diagonal at the same time. All right, so I know this 2-1, there's not even any homework in, it's just making sure that everybody has seen the basic vocabulary of what we use to talk about matrices. Everything that we're going to do coming out of 2-2 and 2-3 is going to assume that you know these words when you see them. Okay, so let's talk about algebra. And in particular, let's talk about multiplication. So we know already that if A and B are the same size, that I have a notion of addition and scalar multiplication. If we're going to do algebra with these things, and you should think of algebra as we're going to solve algebraic equations, just like when we learned algebra in middle school. I want to have a set of rules I can use to solve equations, which means I'm going to need to know something about multiplication and hopefully division, whatever that's going to look like, because that's how I'm going to solve algebraic equations. So I'm going to define matrix multiplication for you, and then I'm going to do an example of a matrix multiplication, and then I'm going to do a very brief justification for why it's set up that way. And then I will point you to some resources if you want to see more. So I can't prove it in this class. I'm just going to have to kind of wave my hands a little bit, but I thought matrix multiplication was the most idiotic thing I'd seen when I saw it defined. Like, why would you do it this way? What on earth would possess you to set up a multiplication this way? So here's what we're going to do. So we're going to suppose that A is m by n. And I'm going to think about A as being a whole bunch of rows. So it's got a row 1 and a row 2. And that symbol means row 1 of A, row 2 of A, and so on. And because it's m by n matrix, it has m rows. These are all vectors, so row vectors. And I need a matrix B. And I want B to be n by r. And I'm going to think of B as being a bunch of columns. Column 1 of B out to, and then column 2 of B, until I get out to column R of B. It has R columns because it's n by r. How many entries are in each row? There's m rows. How many things are in each row? N of them. There are R columns. How many entries are in each column? N of them. So we're going to take this multiplication by forming dot products of rows with columns. I need this number to match that one, or the dot product justification is not going to be defined, right? So A times B, we define AB by A times B is row 1 of A down to row m of A, column 1 of B out to column R of B. And I take the product. The first entry of the product is the first row of A times the first column B. So in the 1-1 entry, I put row 1 with column 1. So this is row 1 of A dotted with column 1 of B. And I move over to the second column here. So I'm still in the first row. So now it's row 1 of A dotted with column 2 of B. And I keep going until I get to row 1 of A dotted with column R of B. And I just proceed that way. The next entry will be row 2 of A dotted with column 1 of B. Notice that the dot product for the 2-1 position in this matrix is that row from A dotted with that column from B. Some of you who've seen this before might have learned it this way, but probably all of you learned the really dumb algorithm where you make the giant multiplications and write huge lists of additions all over the place. And if you haven't seen this before, then you're lucky, because you can learn it the right way. And the last entry out here will be the mth row of A dotted with the rth column of B. So let me do an example of what this looks like. and then I'll try to explain why we ever came up with this definition for multiplication, because this doesn't look natural in any way. That this would be the thing that you would do. So let's just multiply a couple of compatible matrices here. How about 1, 2, minus 1, 3 times, this is a 2 by 2 matrix, and we'll multiply it by, say, a 2 by 3. So 1, 0, 1, 1, 1, 2. 2 by 3. These are going to be compatible. A quick check for compatibility is, since I'm going to be forming dot products of rows of this matrix with columns of this one, that looks like it makes sense because the entries here have there's 2 entries here and 2 entries here. I expect the output matrix to be 2 by 3 because there are 2 rows that I'm combining with 3 columns here. So the way I'm going to calculate this is, I'm going to write it out once in full detail. The first entry is 1, 2 dotted with 1, 1. First row, first column. Then first row times the second column, which is 1, 2 dotted with 0, 1. Then first row times third column. 1, 2 dotted with 1, 2. Then second row times first column. Minus 1, 3 dotted with 1, 1. Second row, second column. Minus 1, 3, 0, 1. Second row, third column. Minus 1, 3 dotted with 1, 2. And you can see that in this dot product, this is all the first row of A, and this is all the second row of A, and this is the first, second, and third columns of the second matrix. So if you do that out, you get, 1 plus 2, 0 plus 2, 1 plus 4, minus 1 plus 3, 0 plus 3, minus 1 plus 6, which is 3, 2, 5, 2, 3, 5. So in practice, you don't actually need to do this step. You don't have to write this down. I'm doing it because I'm being extra careful to show you guys the first time how this is defined. I think that the first obvious question that you should ask when I show you this multiplication is one I've already said a couple of times here, which is, why the hell would you do this? Like, what good is this? So the reason that we set up our matrix multiplication this way is that when I write down a linear function, so if I say f of x is linear, remember that meant that f of ax plus by was equal to a f of x plus b f of y. It turns out every linear function is actually just multiplication by a matrix, all of them. If a function is linear, it means that I can think of f of x as being equal to a times x. So if I had a second linear function g that was also linear, then that would mean that g of x would also be the same as multiplication by some matrix. I'm not going to tell you at all how to find these things yet. I'm just telling you you can find them. And the idea of matrix multiplication is, if I took these two functions and I composed them, if I took f and I composed it with g, so that I was looking at f of g of x, this is also linear. The composition of linear functions is linear. And that means this would have a matrix that represents it. It would be equal to c times x. But I really want the matrix that represents f composed with g to be built from the matrices that represent f and g individually. And this specific definition of matrix multiplication guarantees that if I compose two functions together like this, that the matrix that represents the composition is the product of the matrices that represented the original functions. So I want my matrix representations to go along with composition of functions, and that requires that we set the multiplication up this way. Now, that is as much as I can say about this. If you want to see more depth, in more depth, like what is going on here, what it means to be a linear function, why these things have matrices at all, I can not more highly recommend a series of videos that 3 Blue 1 Brown did on the essence of linear algebra that does a very good job of talking through this stuff in a way that I'm not going to have time to do in this class probably. Certainly not in this period. And because this class is so compressed, there's going to be a bunch of ideas that I can point to that I can't prove. And this is one of them. Okay. All right. So I'm going to show you a couple of annoying features of the multiplication of matrices. The first of which, if it's a multiplication, it sure would be nice. I mean, we have this magic number 1 that when I multiply it by other numbers, it leaves them alone. So let's look at something like this. 1, 2, 3, 4 times this. Just as practice. So if you're doing this quickly, and you were thinking about dot products, the dot product of the first row with the first column is going to be 1 times 1 plus 2 times 0. The dot product of the first row with the second column is 1 times 0 plus 2 times 1. 3 plus 0. 3 plus 4. Oh, look at that. 1, 2, 3, 4. We got the same thing back again. Oh yeah, 0 plus 4. So we took a matrix, we multiplied it by this magic thing, and we got the same matrix back again. This is sort of our matrix version of the number 1. So this is the multiplicative identity. And it's also called the identity matrix. It's a diagonal matrix with all 1s on the diagonal.
So if we multiply something with the diagonal in the other direction,
Then all hell breaks loose. You should try it. See what happens. What's that? Oh, no. Division is the worst. I'm just going to tell you up front. The notion of division and multiplication is going to be awful. And I'll tell you, I'm going to give you some of the reasons why you might believe that matrix multiplication is complicated. So if I wrote down 2 times 3, you would say that's equal to 6. In fact, let's make this even, yeah, that's right. If I wrote 3 times 2, without hesitation, it's obviously equal to 6, right? Multiplication's commutative. 2 times 3 is 3 times 2. If you know the fact one way, you know it the other. You learned this in elementary school, right? Like you can always reverse the order of multiplication, doesn't matter. Okay, so let's take a look at 1, 1, 0, 1 times 1, 2, 3, 4. That's going to be equal to 1 plus 3, 2 plus 4, 0 plus 3, 0 plus 4, or 4, 6, 3, 4. Now I'm going to do it the other way. I mean, everybody knows that multiplication is commutative, right? So we already know what the answer is going to be, clearly. And we get, 1 plus 0, 1 plus 2, 3 plus 0, 3 plus 4. Which gets us 1, 3, 3, 7. Oh, please. AB is not equal to BA. So now we have to do algebra in a number system where if I change the order that I multiply things in, I get different answers. A times B is not equal to B times A. That means, yep.
Also, sometimes you do it in the other example.
Oh, there's all kinds of examples where you can't even reverse it. It doesn't even make sense to do it the other way. Yeah, this is a great observation. If I have the example of say a 2 by 2 matrix and I'm A and I multiply it by a 2 by 3, that multiplication makes sense because the number of entries in each row matches the number in each column, right? But if I flip these, now I've got a 2 by 3 times a 2 by 2. Those numbers don't match. This is not defined. But even when it is defined, as in the case with these square matrices, they're just not equal to each other. Ugh. That means all the things we know about algebra are lies. So for example, What's this equal to? X squared minus y squared. What's this equal to? Well, I'm going to FOIL. A times, remember, order matters now, right? That A is on the left. So it's A times A, and then we're going to have an A times AB minus B times A minus B times B, which gets us A squared plus AB minus BA minus B. Oh, crap. Even all of our basic rules of algebra fall apart because things don't cancel anymore. When we start working with these things symbolically with algebra, matrix algebra is way more complicated than numerical algebra because matrix algebra does not let you cancel this. Symbolically, I can write this down with the same rules, but when I start multiplying with an A on the left times a B on the right, I have to write that with A on the left and B on the right. The symbols, the order symbols are in matter now. You really want to test your logic here. Start doing something like do like A plus B to the third and see what you get out the other side of that. That'll be a fun exercise. All right. So more than that, we also have, and I'll point this out now. I didn't in the last class, but this will be the last thing I point out here today. We have the following problem that comes along with this as well.
If you did B plus A, if you switch the second one to B plus A, then it then cancel out?
No.
Really?
Nope. You can't get it. I can have ABs and BAs always, no matter how you set it up, right? All right, more complicated than that. If you remember back to when you learned systems of equations, you learned about inconsistent and consistent equations, and also equations that had infinite solutions, systems of equations where there were infinite solutions. So what does that actually look like in the land of matrices? So you guys told me earlier that when you were solving an equation like this, you didn't divide. I mean, you did, but what you did was you multiplied both sides by the multiplicative inverse of 2, which always exists. Every number has a multiplicative inverse. Isn't it great that you can do algebra because there's always multiplicative inverses, and so no matter what equation you can write down, you can always just multiply by the inverse of whatever you're stuck on to your unknown and get an answer. Unfortunately, if I have a matrix equation, suppose this was n by n, this is n by 1, so that this is n by 1. If this was known, and this is known, you'd really want to do some kind of divide by a, which really means you'd want to multiply both sides by the multiplicative inverse of a, which unfortunately a lot of times does not exist. So it's possible to write very easy algebraic equations with matrices that you can't do algebra on. So a lot of the methods we're going to learn in here are going to correspond to, hey, if this had an inverse, we can find it. If it doesn't have an inverse, how do we solve the equations in that case? So what we'll talk about next time is how all of this stuff is used to represent systems of equations. And we'll start looking at the sets of techniques that we use to solve systems of equations using the tools of matrices. So essentially we'll be going through Gaussian elimination again, if you've seen that in the past. All right. Oh, I do have an additional office hour tomorrow morning. I'll be in my office from 10 to 12 if you want to stop by.